All right, today we're cracking open a scientific paper that does more than just show us how to build a better laser. It actually uncovers a really surprising secret about what it takes to get things perfect at an almost impossibly small scale. So let's just dive right in. The main question for any researcher in this space is pretty simple, right? How do you make a laser better? You want more power, you want it to be more stable, more efficient. It's this constant push for improvement. But what this research shows is that the answer isn't as simple as just, using better materials. The big twist, and this is what makes this so fascinating, is the discovery that a laser's performance can change dramatically depending on exactly where on a silicon wafer it's built. Okay, but before we get into the how, let's spend a minute on the why. I mean, why are scientists working so hard to build these very specific kinds of lasers in the first place? Well, this is all about something called terahertz radiation. It's this type of invisible light that's kind of sandwiched between microwaves and infrared light, and it has some absolutely incredible potential uses. We're talking everything from next-gen defense and security systems that can literally see through walls, to studying the chemistry happening between distant stars, and even brand new types of medical imaging. So what's the catch? Well, as useful as this tech could be, actually creating a terahertz source that's both powerful and stable has been a massive headache for engineers for decades. And that is the exact problem this research is trying to crack. To really understand what they came up with, we need to kind of pop the hood and take a peek inside the laser's engine to see how this amazing piece of technology actually works. So at the heart of this thing is what's called a quantum cascade laser, or QCL. Now, the best way to picture a QCL is to imagine a microscopic, perfectly controlled waterfall. But instead of water, it's a cascade of electrons. So here's how that little waterfall creates light. First, a bunch of electrons get shot into the system at a really high energy level. Then they start to fall, cascading down this series of super thin layers of material, kind of like steps on a staircase. And here's the magic. With every single drop from one step down to the next, an electron lets go of a tiny bit of energy, and poof, out comes a particle of terahertz light. So, knowing that the laser's engine is this electron waterfall, the researchers behind this paper set up a really simple but totally brilliant experiment. They asked a very straightforward question. If this active region is the engine, does making it thicker, giving the electrons more steps to fall down, make the laser more powerful? It's a pretty intuitive idea, right? A bigger engine should mean more power. And you've got to understand what they mean by thicker. They made the active region 23 micrometers thick. For perspective, that is less than half the width of a single human hair. The level of precision we are talking about here is it's mind-boggling. So, did the thicker engine actually work better? Well, the first results showed that the answer wasn't a simple yes or no. It was actually a trade-off. And you can see that trade-off right here. The thicker 23 micrometer lasers, they were way better at producing these short, really high-power bursts of light. But the thinner lasers, the ones around 10 to 12 micrometers, they were the champs at producing a stable, continuous beam. Turns out the thicker design was better at trapping the light for a powerful punch, while the thinner one was better at getting rid of heat, which can kill performance. So the first big takeaway is that the best laser really just depends on the job you needed to do. But, and this is where the story gets really interesting, this finding wasn't even the most surprising thing the researchers found, not by a long shot. This is where the real mystery started. It led to a discovery that had less to do with the design of the laser and a whole lot more to do with how it was made. As they were going through all their data, the scientists spotted something weird. Lasers that were supposed to be completely identical, built with the same thickness on the very same wafer, were giving them wildly different results. Something else was going on. This chart shows you exactly what they found. It is stunning. A laser's power depended entirely on where on the circular manufacturing wafer it was made. So look at this. A device built near the center puts out over 57 milliwatts of power. But another one, just 8 millimeters closer to the edge, produced only 3.1 milliwatts. That is a performance collapse of over 94%. The paper's author, Hoja Sharma, chalks this up to what he calls a significant inhomogeneity. That's really just a scientific way of saying that the material wasn't perfectly uniform from the center of the wafer out to the edge. So what was this flaw? It came down to these microscopic bumps called interface roughness. Okay, so think back to our electron waterfall. What this means is that the steps of the waterfall got bumpier and less perfect the closer they were to the edge of the wafer. And those tiny, tiny imperfections were enough to totally disrupt the flow of electrons and just cripple the laser's performance.
So, what do we take away from all this incredible science? Well, it offers us nothing less than a new blueprint for how to build much, much better lasers.
Okay, let's just quickly sum up the key lessons. 1. If you need high power pulses, you want a thick active region. 2. For a steady continuous beam, go thin. 3. And this is the big one. Location is everything. You have to build your device at the center of the wafer to get the best results. And finally, this whole study just proves that at this tiny scale, microscopic precision isn't just nice to have, it is literally the difference between a breakthrough and a total failure. When you put it all together, this study gives engineers a crystal clear roadmap. It tells them not just how to design a laser for a specific job, but maybe even more importantly, where to build it to make sure it actually works the way it's supposed to. This is how the next generation of terahertz tech gets made.
And really, this discovery points to an even bigger idea. If a few microscopic bumps, completely invisible to the human eye, can have such a massive impact on performance, it leaves you with a pretty exciting question, doesn't it? What other world-changing technologies are just sitting there, waiting to be unlocked by the next tiny little discovery in manufacturing?